Thank you for coming, everyone. This is an introduction to AutoML. My name is Akshat Vora. I'm co-presenting with David Lepzelter. And today we'll be talking about what AutoML is, give you a quick idea of how easy it is to use AutoML, and then talk a little bit about what goes on under the hood, and then finally explainability. Quick show of hands, how many of you have actually worked with machine learning technologies before in any capacity? That's a lot of you. And then how many of you with SQL? All right, even more. So before I start talking about AutoML, I want to speak about integrated ML, or IML. And this is InterSystems machine learning platform, right? So it is a platform that consists of three providers: AutoML, H2O, and Data Robot. And the idea here is that you can build predictive models without the knowledge of popular frameworks such as Python or R by simply using SQL commands. And so you can use a handful of keywords that we've specially introduced with IML in order to create, train, and then finally predict using these models. AutoML is one of the three providers within IML. H2O is the other one that is also included for free, while Data Robot is a subscription-based model, also within IML. Now, traditionally, what happens with a machine learning pipeline is, as probably a lot of you are familiar, you typically have the first step, which is data acquisition. So that's collecting data from various sources, perhaps, consolidating them all into one file, like a CSV, or in the case of IML, perhaps a SQL table, and then eventually preparing it to build your model. So once you have this data all in one place, the next step is to prepare the data, to clean it, to make sure that the engine understands the data types of the column. So data preparation could include things like removing outliers or making sure that we deal with null values appropriately. The next step is feature engineering. So what happens with a lot of machine learning models is that you can aid the predictive process by taking two existing columns and combining it in a certain manner to create a third column. And this column may provide a certain level of insight that the other two columns could not to the algorithm. Feature engineering is the last step before the data is prepared. And once that's done, we move on to model selection. So a lot of algorithms, a lot of providers, including AutoML, consist of multiple models. So let's say we have classification, right? And you could have a neural network model or a logistic regression model, random forests. Multiple such models are trained on data in order to identify the best possible model to train all of your data on. For instance, let's say that we have several TB worth of data. It wouldn't be practical to train all of your models on all of this data. So you'd subsample some of that data, train all of your models on it, pick the best model, and then train the rest of the data on that one model. And that's the model training step. And by this point, your model is ready to be deployed and for predictions to be made on it. So this is the traditional ML pipeline. Parts of this may be iteratively conducted, and model deployment is typically the last stage. What AutoML does here is it abstracts out a good part of this entire pipeline. So as a data owner, you'd be responsible for acquiring the data and then deploying the model. One caveat that I want to mention here is that the data preparation stage could always use some help of the data owner. And what I mean by that is, as the data owner, you have likely a lot more domain information. So you'd know what kind of data you're dealing with, what columns are completely irrelevant, or what rows are not necessary at all. And the important thing to remember here is that when you're using AutoML, it's best for the data owner to work with AutoML in order to provide for the best results. So while AutoML does do some kind of data preparation, it's always good for the data owner to have some kind of involvement in it. So I want to not talk much about AutoML, but want to show you what an example looks like and how simple it is to really create and train a model. And again, probably as a lot of you are familiar with, supervised machine learning has two broad two tasks, classification and regression. Classification is assigning a discrete label to an input row of data, whereas regression is doing the same thing but with continuous values. So for example, if you have patient data and you want to classify a patient as diabetic or not, or as in the example we'll be using, whether you want to classify a vehicle as a truck, car, or bus. Both of these would be categorized as classification, whereas predicting house prices based on the number of rooms, square footage, et cetera, would be a regression problem. AutoML can handle both of these, but I'll be talking about a classification example today. So like you can see, we have a pretty small table here, really, just 14 rows of data. And there are 4 independent columns: number of doors, the weight of the vehicle, the number of passengers, and the color, and 1 dependent label column, vehicle type. And if you notice, some of these rows have missing values or outliers, like 40 doors for row number 3. And we'd expect AutoML to be able to handle this to a certain extent. So here's a short demo wherein I'm typing out a few commands, and we'll go through each of these commands later really quickly. So once we have our data in a SQL table, let's say it's called vehicles train, all we have to do is specify the name of the model and the column that we are predicting, and then the name of the table that contains the test data. The next step is training the model. This is usually what takes a while. In this case, of course, it's a small example, so it shouldn't take too many seconds. But once that is complete, we'd move on to validation. I'll explain what validation is for those of you who don't know. But validate model, again, really simple syntax. Validate model, model name. And then you specify the name of the table that contains the validation data. And by the end of this, you'd expect to have a table that consists of validation metrics. That helps you determine how good the model that has been trained really is. There's a better view of this in the management portal, but the important value here, besides the precision recall F measures, is the accuracy at the bottom. I'll talk about that as well. And the last step is actually making predictions. So once you have this trained model that you're satisfied with and have validated it, you can start to make predictions and look at the results at the end. So this is the test table or the prediction table with 4 columns that we had defined before, and then the predictions. So going through the step-by-step, the first stage is not here, creating a model. Very simple, create model, name of the model, the column that you want to predict, and lastly, the table from which the training data is being pulled. Now, the default provider is AutoML, but if you wanted to swap your provider to Data Robot or H2O, you could do that using a configuration statement even before this. But since this session focuses on AutoML, this is our first step. The next step is training. What training here involves is model selection and then finally model fitting. So for classification, we look at 3 models. AutoML looks at a logistic regression model from scikit-learn, a random forest classifier, and a Keras neural network. It trains a subsample of the data on each of these models. And based on the model that returns the best accuracy, it goes ahead and trains all of the data using that model. This is ideally the most time-consuming step. The next step is validation. And the reason this is so important is because you want to know how well your model really has fit the data. So after training the model, let's say that you end up testing the model on the training data itself. What's likely going to happen is that you'll see great results, right? Because the training process has seen that data, has likely fit very well to that data, and is probably not good enough to generalize to unseen data. And in order to not fall into this trap, you want to validate your model on some data that it has not seen before. So let's say we hold off some data from a training set, let's call it the validation set, vehicles validate. We know the answers to each of the rows, right? We know what each row is classified as. And we pass this data in using the validate model command. Validate model vehicles simply computes these scores that we saw before. Precision, recall, and F measure for each of the 3 classes that we're looking at. And then at the end here, you see accuracy. And that's probably the most intuitive measure here, which is the number of samples that have been correctly classified divided by the total number of samples that we attempted to classify. So let's say you are satisfied with this model, and you want to go ahead and start making predictions on it. For this, we have the predictions table, which clearly does not have the last column, because we don't know what the results are. Again, this has a few missing values here and there, probably a few outliers. And with a simple select command, which uses the predict keyword, you can try and predict what each of those rows will be, pulling the data from your test table, just as with the create and validate commands. And then at last, you have the predictions. So again, one could, in such a small example, go through each of these predictions and intuitively try and say that, OK, this row does look like a car, and this one does look like a truck. But when you have several thousands of rows, you really do want to perform that validation in order to make sure that you're not overfitting. So that was it for the example. There are a few more keywords, such as the using keyword and a bunch of other keywords that you can use in order to tweak the way that the model trains. And that's all available on the documentation page. But for the sake of simplicity, this is a very easy way in which you can train and make predictions. The last part I want to talk about is what's going on under the hood here. There are 3 broad stages: the pre-processing, the training, and the predictions. Pre-processing consists of several other steps besides these, and I'll only speak about a small sample piece. But just to give you an idea, we use a lot of open source functionalities such as TF-IDF factorization or scale invariance. So the first step is identifying what each column is, what the data type is. Because you have your data stored in Iris, and AutoML works in Python. So when this conversion takes place, AutoML determines whether a column is a categorical data type or a numerical data type or a text column or something else. Now, once it does that, it does fill in missing values for certain columns. So for categorical columns, for example, it fills in the mode of the data. Numerical columns, the mean. Scale invariance is very important because you don't want your model believing that a certain column is more important than another column just because they use different units like kilogram and grams, right? Because a lot of models use variance in data in order to assign importance to columns. And so scale invariance normalizes each of these columns to make sure that they're all treated equally in that sense. We have TF-IDF factorization, which is assigning importance to text fields. So for example, if you have several documents that consist of articles like the, and an, clearly these words aren't as important as contextual words like perhaps Ferrari in a document that talks about cars. And so TF-IDF factorization assigns importance to keywords. So these are all transforms that are performed. Multi-hot encoding is another interesting feature. Let's say you have 2 patient records, and they both have a column that speaks about the allergies that a patient has. So let's say patient 1 is allergic to dairy and soy, and patient 2 is allergic to soy, dairy, right? They're just ordered differently. Multi-hot encoding uses a bag of words technique to split up these lists into different columns, which typically the data owner needs to do, but in this case, AutoML handles it. And then the last step there is preserving these transforms for predictions. So we want to make sure that when you go ahead and make predictions on a certain row of data, it goes through the exact same predictions that the training data has gone through, so that the model understands what it's looking at. And the last stage here is training and model selection. So once a model has been trained, it is persisted in memory until the next model is trained for you to perform one of two possible functions, probability and predictions. I'll talk about that in the next slide, but the idea is that we save these training models and use them until you train the next model. The way that these models are trained is, the first step is, again, like I mentioned, between choosing classification and regression. So this is also something that AutoML does by looking at the label column and determining, based on a certain set of rules, including what fraction of the data is unique, what is the data type of the label column, things like that. AutoML decides whether or not this is a classification problem or not. Another interesting thing is cross-validation. Probably come across it a number of times, but it's segmenting the training data into various chunks so that you can minimize the training bias by looking at several different parts of the training data and taking a sort of average over it. And then a new feature that has been introduced is training modes. So this is sort of a guideline to AutoML where you can tell it, based on your preferences, whether you want to optimize for accuracy or optimize for time. So perhaps some of you may have the entire day to train a model, but some of you may only want to give it an hour on whatever resources you have. You could choose the timed training model, specify the number of minutes, and that would serve as a rough guideline for AutoML to try and adhere to that timing. And then the last stage after the persistence of the model is calling predict or probability. Predict we saw already. Probability is trying to assign a set of probabilities to a given class. So let's say you had a classification problem and you wanted to know what is the probability that all of these data rows are cars, right? So you get one answer for every row of data saying that the probability of this row being a car is 40%, this one is 60%, and so on. And so using these two methods essentially is the last part after model deployment. Now I'd like to hand it over to David to talk about explainability and interpreting data points.
Thank you, Akshat. So I'm Dave Lepzelter. I'm a data scientist here at InterSystems, and I'm going to give you a sneak peek at a feature that we're adding to integrated ML, most especially AutoML, but also the others, which is explainability. At the moment, it's still early in beta, but we are working to get it into all new Iris installations with integrated ML. So explainability is a big subject. I'm going to start with a problem it's intended to solve. How important is the prediction that you're making? I've worked in fields where it doesn't really matter what any given prediction is. It's a nice little add-on, and if somebody gets a prediction wrong, no big deal. Move on to the next one. We make millions of predictions every minute, and none of them really affects anybody too badly. Or other fields, you can get a prediction that is off and is acted on, and that will ruin somebody's life. If you work in healthcare, finance, any number of government agencies, chances are you've got actual people checking over almost any decision, and that's both because you care about getting it right and because the consequences of getting it wrong are really, really awful. And so in these cases, it's not really enough to say, the model says this person has an 80% chance of having cancer, or the model says this person has a 40% chance of defaulting on a loan. There ought to be an explanation. There ought to be a person still at the helm saying, yes, this makes sense. Click, we're going to prescribe this person anti-cancer meds. Click, we're going to approve or deny the loan, etc. And in that case, that person needs some way to be able to trust that the algorithm is actually giving the right answer. And for that, they need the algorithm to give them why it gave that answer. To do that, we are going to use a framework called SHAP, Shapley Additive Explanations. And we're putting that framework into the model training and then into the prediction as an option. So if you just use the straight up stuff that Akshat was saying earlier, you will still get exactly the same thing, but we're also adding an extra thing to the predict and probability items that he mentioned to give you explanations. So here's a flow chart of how the training part works. You take the raw data, you prepare it, or AutoML prepares it. It trains the model. It takes the trained model and the prepared data, and it trains an explainability model. That, of course, adds a little bit of extra time to the model training, which is why we are planning on having that be something that you can opt out of if you choose. But for the most part, we tend to assume that everybody would like to have explanations, so that's going to be the default. Eventually, you have the explainability model. Here's how it will work with integrated ML once it's been trained. You get all of this. You get either predictions or predictions and explanations. And if your model starts not performing well, then, well, you retrain the model and the explainability model. Here's what the SQL syntax looks like for the explainability. So like predict explain. You have your model name that Akshat was talking about earlier. You've got the table name, which is the vehicle's test or whatever it was. And you've got a where clause where you can just specify which columns that you want to actually explain. And this will return a list of the specific columns for each row that contribute to the overall prediction or probability. I'm sure you'd like to see an example. So for the sake of making this easy, I'm using the same data as Akshat and almost the same model. This one is just the probability that the given row is a car, not a full classification. That's for ease of showing off the explainability part, which gets more complicated with extra possible columns. So we're just using almost the same model, adding the explanation part to the end. And here is the one data point that we are trying to predict on, or trying to explain, rather, predict and explain. This is a 4-door, 4-passenger vehicle. Weight is 6,000 pounds. Color is black. You and I probably can guess that this is a car, just based on all of the other things in that earlier table. But it's good to see what explainability says about it. All right, you'll see that the top contributor to the overall probability is that the weight is 6,000 pounds. That contributes about 32% to the overall probability that the model says this is a car. Second, the number of doors is 4, which contributes about 19%. And number of passengers is 4, which contributes about 10%. Now, all of these put together do not actually add up to the 83% chance of this being a car, which is what this model says, because there is a default that it starts at. It starts at 22%, and then you add up these to get the 83. You'll notice that color doesn't come into play. If you're curious about why, I'll answer the question, but you should know that normally it'd just say the contribution to probability was something like 1%, something that just looks obviously unimportant. Any questions on explainability before we get to the wrap-up? No. No, this is model independent. This is essentially modeling the model using the data. And so it has no reliance on model type.
Minimum amount of data you need to get it to be able to do this kind of prediction also?
Realistically speaking, no, but yes. You'll find that anything that it will actually train, it will also explain, but the size of data that we're talking about here is at the extreme low end of what can possibly give you decent results. And so once you start actually exploring what that does with actual data, you'll see, oh, well, that's just not large enough. But what exactly that entails is an enormous subject. And it depends greatly on type of data and what kind of results are acceptable. So, yeah.
Just to follow up on that question, because this is a big topic. Will this tell you that you do not have enough test data or will it give you a flag to say that you can't run something that's statistically significant?
So, the primary way to get that is the validation metrics. You get that from a validate command. Right. You'll get bad accuracy or bad one of the other dozen scores, and that will tell you that you either did something wrong with the data prep in the first place, or that you just didn't have enough data.
Works for regression also?
This works for regression. This works for the probability part of the classification. So either one.
That's all we have for you. So just to summarize, we looked at how SQL can be used to create these predictive models, and a quick look at what went on under the scenes. And then, again, just the syntax that we could use to create these models, the persistence of models, and then explainability and interpreting results. And post this session, we have a couple of other machine learning sessions at this summit. There's integrated ML advanced topics and cloud IML. And you can always meet one of us after this session or anytime through the summit to talk more about it. And we'll have questions afterwards as well. And the docs are pretty comprehensive. So if you feel confident enough to, you want to try something out, and the docs are the best place to start at. And here's our contact information in case one of you wants to reach out to us, post-summit. So, thank you. And any questions, please let us know.